All right, here are our examples for our work section. So make sure you have read the section in the book and print out your notes and kind of have read through those. And here we go, we'll fill in those examples. All right, so the first one, a spring has constant K equals 5/3. Find the work done in stretching the spring 6 inches beyond its natural length. So, you know, up there above this example, you know, I gave y'all Hooke's Law and what it says, and we're going to use that here. So what we have to do is find the force first. Okay, so F equals K times D. Okay. All right, so that was that Hooke's Law. So let's plug that in. All right, so F equals K is 5/3, it tells me, okay, and then X is going to be that D. All right, so the work done in stretching the spring is going to be, all right, I'm going to go 6 inches beyond its natural length, so I'm going to go 0 to 6, okay, and then I'm going to integrate 5/3 X dx. So let's do that. We've got our 5/3 X to the first power. So remember, I'm just using that basic power rule, add 1 to it, and I'm going to divide by the new power of 2, and dividing by 2, same as multiplying by half. So I end up with 5/6 X squared, and I want to integrate it from 0 to 6. So 5/6 times 6 squared, and then this is just going to go away because it's 5/6 times 0 squared, which is just going to be 0. So one of those 6's will cancel, and I end up with 30 inch-pounds. Okay? All right, so let's keep going. Second example goes with it. With that first one, find the work done in stretching the spring from 3 inches to 6 inches beyond its natural length. So I'm going to have the same thing to integrate it, but instead of just going straight to 6 inches beyond its natural length, since I'm going from 3 beyond to 6 beyond, I'll have this integral. And I still keep that 5/3 X dx. And so we've just integrated it. We know it's 5/6 X squared, and this time I'm going from 3 to 6. And I'm going to start skipping some of this work because at this point you guys know what to do here. And I'm going to save some time and on some of these just going to go straight to the answer. But when you plug it in and do this math out, I got 22.5 inch-pounds. All right, next one. A force of 9 pounds is required to stretch a spring from its natural length of 6 inches to a length of 8 inches. Find the work done in stretching the spring from its natural length to a length of 10 inches. All right, so the difference in this one and the other one is we don't have K, okay? We've got to find K. All right, so this is what we're going to use. This is where we're going to use what they told us in the beginning. All right, so f of x is equal to k times x. All right, and then we're going to do this. X is going to be the length you stretched. So if you read that first sentence, it says a force of 9 pounds is required to stretch the spring. So 9 is required to stretch the spring from its natural length of 6 to a length of 8. So I stretched it 2 inches. And so if I solve for K, that's K tells me K is 9/2 now. All right, so the work done would be integral. All right, so let's think about we're going from what to what. So I want to find the work done in stretching the spring from its natural length, which was 6 inches, okay, to a length of 10 inches. So I'm stretching it from 0 to 4 because that's how many inches I am stretching it, and we know it's kx, so 9/2 x dx. All right, so if we integrate that with the power rule, again, we add 1 to it. Dividing by 2 is the same as multiplying by half. So I get 9/4 x squared from 0 to 4. And I'm going to let you guys plug that in. But when I did it, I got 36 inch-pounds. Okay. So make sure you try some of those spring examples that you got. Oh, wait, this has a part B with it. Find the work done in stretching the spring from a length of 7 inches to a length of 9 inches. So we know what we're going to integrate. This part is just figuring out from what to what. So remember, its natural length is 6 inches. Okay, so the natural. So I'm going to go from 7 to 9. So that's going from 1 over to 3 over of that 9/2 x dx, which we know when you integrate it, you get 9/4 x squared, and this time you want to go from 1 to 3. So again, you guys can plug that in and you get 18 inch-pounds. Okay, so now make sure you try some of those spring problems out of your book. All right, so let's keep going and let's switch a little bit to different kinds of word problems that involve work. All right, so let's look at this one. A 20-foot section of rope weighing 2 pounds per foot is hanging from a crank. How much work is done in winding up the entire length of the rope? So I gave you some notation in your notes, and so you can see what we're calling this stuff as we go along. Okay. All right, so our formula is work equals integral from C to D, all right, of delta F sub K, which if you look at that, that's, you know, the force required to lift that slice, okay, times Z sub K, okay, which Z sub K is the distance that that slice is lifted. Okay. It's going to end up being a dy because it's hanging over a building or hanging wherever, and you're going to move that up and down. All right, so let's fill in what this stuff is. All right. Delta F sub K, all right, that's going to be the weight of the rope times dy. All right, so it tells me that the weight of the rope is 2 feet, all right, 2 pounds per foot, it's dy. All right, now let's figure out what is Z sub K. All right. Z sub K is the distance lifted, and it's the distance lifted at any point. Okay, that's going to be 20 minus y, because what you're thinking of is you've got this rope hanging, okay, and you know the rope is 20 feet long. So at any point, you know, if I want to know how high it is, if I want to know this part, okay, well, I take the whole thing 20 and I subtract off the y, and that's going to get me how much I have lifted that end point up. So now that I know what that stuff is, I can plug it into my formula. Okay, so work is equal to, all right, now I'm going to go 0 to 20 because it says wind up the entire length. Okay, and it is delta F sub K, which is that 2 dy, which we found, times Z sub K, which is the distance lifted. So that's 20 minus y. All right, so let's get this a little bit better. So if I take the 2 and distribute it, well, 2 dy and distribute it, I would get 40 dy minus 2y dy, but, you know, we just kind of put that 1 dy at the back, and it's understood it's going to go with both. So if I integrate it, I get 40y minus y squared, and I'm going from 0 to 20. And if you plug that in, you get that the work needed is 400 foot-pounds. Now, pretend you hooked your little brother to the rope and hoisted him to the top. What's the work required to lift the 65-pound boy to the top of the crank? And I probably should, well, here we go. You want to look at it like this. All right, if you got to find the, you got to add in the work for the boy. Okay, so the work for the brother is just equal to F times D. That very first one that is not in one of these examples, but it's typed in your notes and in that red. And so that's the weight of the boy, okay, 65, and we were lifting him 20 feet. So if you multiply that, you get 1,300 foot-pounds. So that's the work for lifting the brother. So when you put it all together total, the total work that you have done, you need the work of the rope plus the work for the brother. So that was 400 that we got before plus this 1,300. So it's 1,700 foot-pounds. of work. All right, and then the last two work very, very similar. You're going to have a shape, and so you want to know those volume formulas, and you're going to have some sort of shape, and we're either pumping water or something out. All right, so let's look at this. A water tank has the shape of a right circular cylinder with radius 10 and depth h. All right, so if I think about it, I have this cylinder, and the radius is 10, right, and it is the depth is 20. Okay. The tank is full of water weighing 62.5 cubic pounds per cubic foot. Find the work done in pumping the water out through a valve at the top of the tank. Okay. So I'm going to take this thing is full of water, and I want to pump all the water out through the top. Okay. So I'm going to kind of label it in steps what you do. All right. First thing you want to do is find the volume of one disc or one slice. Okay, so I'm thinking about just one slice, and I want to find that volume. So the volume of a right circular cylinder is pi r squared h. All those volume formulas can be found on the inside cover of your book. All right, so if I plug it in, it's going to be pi times 10 squared. Right? You're going to use dy for the height of these, okay? Okay, because that's going to change, you know, depending on where you are with that slice. So the volume of the disc or the slice is 100 pi dy. So it's the first thing you need to do. All right, and I'm hoping I can fit it all on the screen. Second thing you need to do is find the increment of work, which is delta F sub k. Okay, so that's the volume of the disc. Hold on, let me write this better. That is the volume of the disc, which we just found, all right, times the weight of the water. So that's going to be, we just found it, 100 pi dy times 62.5. And so I get that delta F sub k is equal to 6250 pi dy. Okay. All right, third thing we want to do is find the distance that is lifted. Okay, so the distance lifted, this thing has a depth of 20. All right, so it's going to be 20 minus y. Okay, same like it was kind of with the rope. All right, so now we can plug into our formula. Work is equal to the integral from c to d of delta F sub k times z sub k. So we found all those pieces, and since I'm pumping all of the water out, I'm going from 0 to 20. Right, and then just multiply those pieces. So we had 6250 pi dy times 20 minus y. It's the easiest thing to do is to pull out that 6250 pi. Okay, and then you're just integrating 20 minus y dy. And then, so that's 6250 pi times 20y minus y, 1/2 y squared, all right, minus 1/2 y squared if you integrated that. And you want to go from 0 to 20. And so then that's 6250 pi. I'll make sure you can integrate this later. I got 200 when I did it. And so if you multiply those, I got 1,250,000 pi foot-pounds. Okay. All right, so let's do another one like this, but has a different shape. An aquarium that is 2 feet long, 1 foot wide, and 1 foot deep is full of water weighing 62.5 pounds per cubic foot. All right, so I'm not the best at drawing these, but you'll get the idea. All right, so I have this aquarium. Okay. All right, it is 2 feet long, 1 foot wide, 1 foot deep. Okay. And then I want to find the work needed to pump all of the water out of the aquarium. So we're going to do the same thing. First thing we got to do is get the volume of the disc. Okay, well, the volume of this shape is length times width times height. All right, so that would be volume equals, all right, 2 times 1 times, remember we're always using dy for the height, so it's 2 dy. Okay, all right, now I need to find delta F sub k. So remember that's the volume that you just found times the weight of the water. So that's going to be 2 dy times that 62.5. So we get that delta Fk is equal to 125 dy. Okay, and then now the distance lifted, okay, find z sub k, right, that's going to be 1 minus y, okay, since it's only, a foot deep. Okay, so now the work is equal to integral from c to d of delta f sub k times z sub k. And so let's plug in. All right, so I again am pumping all the water out, so I'm going from 0 to 1. All right, and then that's going to be 125 dy times 1 minus y. All right, so again, to make my math easier, I'm going to pull that 125 out on the outside, and I'm going to integrate from 0 to 1 of 1 minus y dy. So that's going to be 125 times, if you integrate 1, you just get y, and then integrate y, you get about negative y, it's negative 1/2 y squared, and I'm going to go from 0 to 1, so you would do that part first, and so that's 125 times 1/2, which equals 62.5 foot-pounds.